Hi everyone, this is Chen from Georgia Tech. I will be presenting two-known flow diffusion in near linear time. This is a joint work with my advisor, Richard Peng, who recently moved to University of Waterloo, and Wang from Google. So we are talking about diffusion on graphs. By graphs, I mean the ordinary graphs with n vertices and m edges. The diffusion is the generic process of spreading mass across the graph to adjacent vertices. So for example, we put some mass on these two dark vertices, and then the mass are spread across adjacent edges to its neighbors, and so on. Diffusion has been used in many graph applications, such as graph clustering. For example, the problem of local clusters wants to find a cluster contains the given initial set of vertices, and this has been used in the first expander decomposition algorithm and the first spectral sparsification algorithms. Using diffusion, we can also find a sparse or balanced cut in graphs. And in the more empirical settings, such as graph learning on graphs, diffusion has motivated some model designs, such as graph neural networks, and they have some recent works on designing diffusion as a layer of the GNN. And also incorporating ideas from diffusion, people has achieved state-of-the-art in node classification tasks. So generally, there's two categories of diffusion on graphs. One is called spectral. Examples includes random walks, page rank, and heat kernels. These are defined using graph matrices, and they all looks like some kind of variation of random walks. And another category is the combinatorial ones. They view diffusion as they use the concept of network flows to view the process of diffusion, and this has gives some results using push relabel and blocking flows. And in a paper by Fontolakis in 2020, they proposed this new model of diffusion called p-norm flow diffusion. So p-norm flow diffusion is modeled as the following optimization problem on graphs. So given some initial supply on each vertex encoded by this vector S, and I want to find a flow to distribute this initial supply to the entire graph, such that respects the sink capacity per vertex. And while doing so, I want to find the flow with minimized p-norm. One can view this problem as a direct generalization of the typical network flow problems, where the total amount of supply is equal to the total amount of sink capacities. So here we have an example of a flow diffusion. So consider this graph with 6 vertices. We have some supplies on vertices A and B. And we want to spread this mass on vertices A and B to vertices with positive sink capacity, such as vertex C, D, and E. An example to spread these vertices is drawn by these blue arcs, such as we spread 1 unit of supply from A through the path A, B to E, and spread the mass 1 unit of mass on B to its neighbor C. So when viewing this distribution as a flow, we can measure its one norm. So for this kind of distribution, this flow is one norm is 5 and its infinity norm is 1. Which, an advantage of this model is that it acts as an interpolation between the spectral diffusion processes and combinatorial diffusion processes. So when taking p equals 2, they show that both theoretically and empirically, the solution to the two-known flow diffusion is similar to the ones using spectral diffusion processes, such as random walks, page ranks, etc. And when solving the p equals infinity flow diffusion, the resulting solution has similar theoretical guarantees and empirical performance as those combinatorial diffusions. In our paper, we show that the problem of finding the flow for two known flow diffusion problem can be done in near linear time. Specifically, we can find the solution up to 1 plus epsilon error in near linear time times log 1 over epsilon with high probability. So our algorithm is actually randomized, and it would be interesting to make it deterministic. And for comparison, the original algorithm proposed has this huge runtime of n cubic times n squared, which is not that nice. So our algorithm we focus on a more general case of the weighted two-norm flow diffusion. That is, we can solve the problem even there's weight on each edge. And our algorithm focus on solving the dual of this problem. By taking the dual, the problem becomes a non-negative quadratic programming problem on the Laplacian matrix. That is, this matrix B transpose R inverse B, where B is the edge vertex incidence matrix of the graph G, and R is the diagonal matrix encodes the edge weights. And for the rest of this talk, we will focus on this dual problem. So when there's no this non-negative constraints, the problem is equivalent to solving the Laplacian linear system that is solved for x such that Lx equals negative d, where d is the demand vector. And there's since the seminal results of Spearman-Chen in 2004, there's a huge line of results that gives near linear time solver for such linear systems. So our idea is very simple. We simply generalize their techniques to the case where non-negative constraint is present. So we adapt this solver framework from Spearman-Chen 2004, and we measure. And there's an important notion of this T of M and K. It's denoted to be the runtime for solving a graph of a size M, and when allowing error up to K. Using this language, we can express our results as the following one-line equation that T of N, 1 plus epsilon, is N times polylog. So the first component of this framework is a Vertex Reduce routine. That is, given a graph with the following structure, that it's a union of a smaller graph of only n over k edges and a collection of trees with roots inside this n over k graph. We show that we can reduce the problems on this graph onto a smaller graph of size only n over k. So, and this is done by iteratively remove the degree 1 vertices from the left-hand side graph. So this means that all these trees are gonna be removed, and the resulting graph is the n over k sized graph. So the simplest case is to remove this degree 1 vertex, and by doing so, we first observe that the first thing we want to do is to encode the cost on this degree 1 vertex u and its adjacent edge to its solely neighbor v. By doing so, we found out that the value on this vertex u is actually a function of its neighbor, and due to the non-negative constraints, this function looks like this Rayleigh function, and we can actually prove that by reducing degree 1 vertices one at a time. We can remove the entire tree and represents the cost on this entire tree as a single function on the value of this root v. And this function, we show that if the tree has size k, the resulting function has size k as well. Specifically, this function is a k piecewise quadratic convex function. And size of k is still too large for us to handle. So we show that since we only require like constant approximation, this function can actually be approximated by another one with only log n pieces. So this concludes our vertex reduction scheme, and we can reduce the problem on this n over k sized graph plot trees to the one of only size n over k. The second component is this edge reducer, and so first we introduced the notion of spectral approximation. So we say another graph H approximates G spectrally with quality K if their Laplacian matrices are K similar. So an observation we have is that by solving for a solution on H with constant approximation, this solution is naturally a O of K approximation on the original graph G. And our work shows that we can construct a spectral approximation of quality K by a graph with simpler structure that is a size n over k graph plus a bunch of trees. And this object is called the J tree. And it first appears in Marjorie Peng and in the context of approximating cuts of the graph. And not only cuts can be approximated, another paper in 2020 shows that such objects can approximate distance as well. And our paper shows that this object can also approximate the quadratic form induced by the Laplacian matrix. So the last component of our algorithm is this quality booster. And the underlying implementation of quality booster is called accelerated proximal gradient method. So considering we are solving this flow diffusion problem on this graph G, and we are also given H, which is spectrally approximating G with quality K. And this accelerated proximal gradient method shows that by solving square root K iterations of the similar problem of flow diffusion on this graph H, and we can obtain a high accuracy solution on the original graph G. So now we can combine all these three components in the following way. So first, we want to solve flow diffusion on this graph G. So first we use edge reduce component to find approximation of G using this n over k size graph plus trees. And then we use quality booster to show that, okay, to solve on G, it suffices to solve on square root of k iterations on this simpler graph. And then on this simpler graph, we can use vertex reduce to show that, okay, we only care about this graph of n size n over k. And then to solve this size n over k graph, we can recursively apply the same algorithm again. So this, by solving the recursion, this gives the desired near linear running time. So for conclusion, our work shows a near linear time solver for a wider class of flow problems beyond electrical flows and p-norm flows. And we also gives a near linear time solver for a class of non-negative quadratic programming problems. And this algorithm can also be viewed as a near linear time algorithm for finding local clusters and whose running time is independent of the conductance of the cluster. And we also show a new way to deal with non-negative constraints on graph problems beyond interior point methods. And we also construct a nicer spectral Sparsifier with some nicer properties. So next we discuss some open problems and future directions. So the first is, can we find a simpler algorithm for two-node diffusion problem? That is an algorithm without the recursion. And the second one is, can we find an algorithm whose running time depends only on the sparsity of S? That is, we only depends on the, if the supply is sparse on the graph, then can our algorithm run faster, or can we have a faster algorithm? And the third is a simple one. Can we improve our algorithm to even faster running time, such as n log n or even n poly log n? And another one is, can we have like algorithm for solving p-norm flow diffusion instead of only two-norm flow diffusion? And the last one is, can we reduce some other graph problems to the two-norm flow diffusion problem, since we have this nice way of dealing with non-negativity constraints and the running time is fast? Can we generalize these techniques to some other problems as well? So that's it, and thank you very much.